San Diego hospitalizations. And so then when you take your difference in differences, it's contributing 0 to that, right? Because it's basically contributing 0 to the change in Los Angeles, 0 to the change in San Diego. So of course it's going to contribute 0 to the change in those two changes, or the difference in those two changes, I should say. Okay, so if this omitted variable ZIT basically differs in the treated and the control regions, but is constant over time, it again is not going to bias the diffs and diffs estimator. So the nice thing about diffs and diffs is there's sort of these two very broad classes of omitted variables that we think it's going to eliminate. So one class is sort of omitted variables that are potentially different have different levels across the treated and control group, but aren't changing over time. The other class is omitted variables that in fact are changing over time, and so would bias our estimate if we just look at the raw change in Los Angeles hospitalizations, let's say, but that we think are changing in equal amounts in both the treated and the control groups. And so then once you take the change for the control group and net that out for the change or from the change in the treatment group, then it again gives you an unbiased estimate. So that's pretty powerful in that it can sort of eliminate these two classes of biases, but it's not like bulletproof, right? So you still have a concern, and the concern is always going to be for these diffs and diffs studies. It's always going to focus on omitted variables that change over time in different ways for the treated and the control group. So if something's not changing over time, then we know it's not a problem. And if something's changing over time but is doing so in the same way for the treated and the control group, then we also know it's not a problem. But you can get problems when there's some omitted variable that's changing over time and it's changing in different ways for both the treated and the control group. So to just make this clear, let's say that there's some omitted variable ZIT whose causal effect on YT is again alpha. And now let's suppose that it's changing by delta star units in Los Angeles and delta star units in San Diego, where these two things aren't the same. So then when we take the difference for the change in Los Angeles hospitalizations, the contribution of that variable to the change in Los Angeles hospitalizations is going to be alpha times delta star. The contribution of that variable to the change in San Diego hospitalizations is going to be alpha times delta star. And then this diffs and diffs, the change in LA minus the change in San Diego, is unfortunately not going to net out to 0. So what we always want is for the bias from this omitted variable, this unobserved variable, to net out to 0. That's not going to happen here, right? Because we have alpha times delta star minus alpha times delta star, which is equal to alpha times the difference of these two deltas. But as I said, those two deltas aren't equal. So that quantity doesn't equal 0, and you're going to end up with still having some remaining bias in your diffs and diffs estimator. So in these diffs and diffs studies, what we're really worried about are these omitted variables that basically might change differently over time in the treated group than they do for the control group. So the idea here, again, so just to bring it back to what I started with, I said that what we'd like to do is be able to basically observe the counterfactual trajectory for Los Angeles hospitalizations if there hadn't been this policy that reduced air pollution. And so what we're doing is saying, well, we think that what we see in San Diego is basically giving us that counterfactual trajectory for what would have happened in Los Angeles absent this policy intervention. But the problem is that if there's something going on in San Diego that's changing behind the scenes, and it's changing behind the scenes in a way that's different in San Diego than it is in Los Angeles, so there's this omitted variable that's changing differently for San Diego than for Los Angeles, then San Diego is not going to really give you a good counterfactual representation of what would have happened in Los Angeles, right? Because there's something different going on in San Diego than there is in Los Angeles. So the last thing that I want to emphasize here or discuss is that it's also possible to implement this diffs and diffs estimator within a regression model. So in practice, this will be something that's kind of important to know or realize, because so what I wrote up for you before, which is basically like, so it was like y11 minus y10 minus y01 minus y00. So this is like delta y for Los Angeles. So it was I equals 1. And then this is delta y for San Diego, which said corresponded to I equals 0. So you can estimate, or you can write down the diffs and diffs estimator this way. But in practice, what happens a lot of the time is that people will instead run a regression that actually ends up estimating this quantity. But if you didn't realize exactly like what the regression formulas were, you wouldn't necessarily know that what they're in fact estimating is equivalent to this differences and differences estimator that I just wrote up here. So let's sort of consider a case in which we have several variables here that we're going to observe or define at least. So we have one variable which measures time, and that's going to be a dummy variable in this case because we just have 2 years. So there's really only 2 time periods. And it's going to equal 0 in the pre-policy period, and then it's going to equal 1 in the post-policy period. Then let's also define a second dummy variable here that we'll call Los Angeles. And this variable, I think you can sort of guess what value it's going to take on. It's going to be equal to 1 in Los Angeles if an observation corresponds to Los Angeles, and it's going to be 0 otherwise. So we only have 2 counties in this like hypothetical simple data set that I set up for you. So 0 is going to correspond to, if Los Angeles dummy is 0 here, then that corresponds to the observation being in San Diego. And then finally, there's going to be this third variable we have here, which we'll call the policy variable. So the policy variable basically is an indicator for whether or not the policy whose treatment effect we want to actually estimate is in effect in county I during period T. And so it's going to be equal to 1 if that policy is in effect, and then it's going to be 0 otherwise. So the critical thing here is to realize that this policy variable is actually identical to the interaction of the time variable times the Los Angeles variable, right? So let's think about what happens when we interact these two variables, time and Los Angeles. So basically that interaction is itself going to be a dummy variable because each of those two variables only takes on 0 and 1 values. It's going to be equal to 1 if you're looking at an observation that's in the post-policy period in Los Angeles, because then both of those variables, both time and Los Angeles, are equal to 1. So that's going to be Los Angeles in 2010. Otherwise, it's going to be equal to 0. But that exactly corresponds to the observations for which the policy variable should be activated, right? Because we know that first of all it's never activated in San Diego, so it should always be equal to 0 in San Diego. And we also know that it's only activated in 2010, right? So it shouldn't be activated in Los Angeles in 2009, and that's exactly what we're getting here. So in 2010, when you're in Los Angeles, this thing is equal to 0, and otherwise, it's equal to 1, and otherwise it's equal to 0. So then let's consider the regression of y on those 3 variables. We're going to regress y on time, on Los Angeles, and on this policy indicator. So if we think about what happens if we look at the pre-policy period in San Diego, we're going to ignore EIT, these unobserved determinants of YIT, because basically we're going to assume that on average those things are going to be equal to 0. But ignoring that, so let's think about what happens if we're looking at the pre-policy period in San Diego. So then we're going to forecast that in expectation at least, hospitalizations are going to be equal to beta naught, right? Because if you're in San Diego and it's the pre-policy period, then time is equal to 0, so that beta 1 falls out, Los Angeles is equal to 0, so beta 2 falls out, and then the policy of course is equal to 0 because both time and Los Angeles is equal to 0, so beta 3 falls out. Then the second thing we can look at is the pre-policy period in Los Angeles. That's going to be equal to beta naught plus beta 2 in expectation. So the number of hospitalizations in Los Angeles before the policy should be equal to beta naught plus beta 2 in expectation, basically because now you always have beta 0 in there, and now Los Angeles turns on, so you have beta 2, but time is still set to be the pre-period, which is 0, so both time and policy are going to be equal to 0. Then you have the post-policy period in San Diego, which is going to be equal to beta naught plus beta 1. So now Los Angeles and policy are set equal to 0, but the time indicator gets set equal to 1, so you just have beta naught and beta 1 left there. And then finally you have all 4 things turned on, right? So you have the post-policy period in Los Angeles. So beta naught is there as always. Now time is set equal to 1 because you're in the post-policy period. So you still have beta 1. You're in Los Angeles, so you have beta 2. And then since both time and Los Angeles are on, it's when the policy is in effect in Los Angeles, you also have beta 3 there. And beta 3, of course, is what we want to estimate here. It's going to be the policy's effect. And so if we think about then sort of reframing this into the diffs and diffs estimator, we would plug in the following quantities. So y11, which is Los Angeles in the post-policy period, is equal to the sum of all 4 of the betas there. Then y10, which is Los Angeles in the pre-policy period, is equal to beta naught plus beta 2 there, pre-policy period in Los Angeles. Then y01, which is the number of hospitalizations or the expected number of hospitalizations in San Diego post-policy, is going to be beta naught plus beta 1. And then y00, which was pre-policy period in San Diego, we said at the very top there is just equal to beta 0 in expectation of these. So you have like, this combination of all these coefficients, some of which are being added, some of which are being subtracted. When you sort of go through, what you end up with is beta 1 plus beta 3 there, because this beta 0 and this beta 2 are offset by that beta 0 and that beta 2. And then you end up with beta 1 here, because this beta 0 and that beta 0 offset each other. And then, of course, the 2 beta 1s offset each other, and you end up with beta 3. So it turns out that the diffs and diffs estimator that we wrote up here before is equivalent to basically estimating this following regression and then looking at the coefficient, the regression coefficient that you get on this policy variable. So what that's going to allow you to do is estimate the diffs and diffs estimator using a regression. So the benefit of that, there's sort of like a couple benefits. One is that it just turns out in the regression package, like it's easier to sort of define a few variables and then tell the statistical package that you want to do regress y on x1, x2, x3. So that's one benefit. The other benefit is once you sort of reframe it into looking like a multiple regression, then you can actually also control for other factors in that regression, right? So we know that the diffs and diffs estimator is netting out omitted variables that are either constant over time or that are changing over time but in the same amount for both the treated group and the control group. But if you had some other variable that you thought was changing, so maybe that like sort of nets out most of the biases that you could think of, but maybe there's like a few variables left that you can think of that are changing differentially. They're changing over time. They're changing differentially for Los Angeles versus San Diego. If you happen to have data on those select number of variables, then you could also include them in your regression. So once you set up the diffs and diffs estimator as a multiple regression, then you can kind of have like the best of both worlds, right? You can get the bias elimination of these particular types of factors that diffs and diffs gives you, and then on top of that, you can also control for some other factors that maybe are changing over time differentially for the two counties, and that therefore aren't being netted out by the diffs and diffs. Lexi? So could you just demonstrate that this doesn't accurately do them? You can control for those variables? You mean then just doing the standard diffs and diffs estimator? Yeah. So if you have some additional things that you want to control for, then that would be preferred to just doing the generic or the simpler diffs and diffs estimator. Because it's sort of like, at one point, I think I said earlier, like, as you add additional variables to the regression, like the predictive power can never go down. So basically, for the most part, you can't sort of go wrong by controlling for additional variables. You can only either sort of maintain, like tread water, like basically the regression might assign a 0 coefficient, and you'll just get the same answer as you did without controlling for them, or maybe it'll turn out they actually are sort of important, and then you get the additional method of controlling for them. So, okay, so generically, in the course, I'm going to refer to regressions that include both time trends and what we call these cross-sectional dummy variables as diffs and diffs estimates, or like diffs and diffs type estimates. So the time trends are being picked up by this time variable, and then when I say the cross-sectional dummy variable, basically I mean an indicator variable for telling you like what county or state or maybe individual you're looking at depending on what type of data you have. So if we have something that controls for that time variable, or regression that controls for that time trend and controls for these cross-sectional identifiers or indicators, then you can basically think of the resulting coefficient on beta 3 or policy that you get the beta 3 there as being like a diffs and diffs type estimate. And the reason is that the time coefficient is basically going to describe how YIT changes over time. So it's going to control for factors that change over time equally for both Los Angeles and for San Diego. It's sort of picking up general time trends in your data. And then the Los Angeles coefficient describes how YIT, how the outcome differs on average in Los Angeles versus San Diego. So the Los Angeles indicator, of course, varies depending on whether you're in Los Angeles or San Diego, but it doesn't vary over time. So it's sort of picking up these factors that are different between Los Angeles and San Diego, but that are constant over time. And so it's going to control for these factors. And as a result, the only factors we're going to worry about are factors that change over time differently for Los Angeles versus for San Diego. And I said earlier that those are the types of factors we'll worry about for diffs and diffs, for generating bias in the diffs and diffs framework. Okay, so then the very last thing that I want to talk about here, which we don't quite have time to talk about today, I think is going to be about statistical significance. So let me just sort of describe this at the beginning, and then we'll go into detail about what it actually means in the next lecture. So the statistical significance of a regression coefficient is basically going to measure the probability that you would observe a coefficient that large or larger if the true coefficient were in fact 0. So let's think about just a very simple regression. We're regressing y and x, and we have some coefficient, some slope coefficient beta 1. In any finite sample, beta 1 is very unlikely to be exactly 0 because when you compute the covariance between two variables, it's very unlikely that would be, even if they're unrelated to each other in expectation, it's very unlikely that the exact correlation will be 0. It's just like if you computed the mean of a variable in a given data set, even though the true mean might be equal to 0.5, let's say, it's unlikely the sample mean is going to be exactly equal to 0.5, right? So if you flip a coin that was fair 20 times, you would expect to get about 10 heads and 10 tails, but in any finite sample, you might get 12 or 13 or 9 or whatever. So you can think of sort of the true beta 1, the true coefficient, as being the one we'd estimate. We had an infinitely sized sample. And what we'd like to do is determine whether our estimate of beta 1 represents this true relationship or some statistical noise. So we estimate a non-zero coefficient for beta 1, but we want to know, does that mean that the true beta 1 is actually 0, or is it just the case that the true beta 1 is 0, but that or I guess let me say that. Does it mean that the true beta 1 is not 0, or does it mean the true beta 1 in fact is 0, but just due to statistical noise we happen to estimate a non-zero value of it? And the answer here, which we'll discuss in a little bit more detail in the next lecture, is that using statistical theory we can derive the distribution of beta 1 under the assumption that the true coefficient is 0, and then test the hypothesis.